In this video, we will take our last look at integration by parts, and in some sense, you can say we've saved the best for last because the type of integral that we're going to look at now is a really tricky type, and it does require repeated integration by parts, but it doesn't work out as nicely as those in our previous videos, particularly if one of our factors is a polynomial. We know eventually we differentiate a polynomial and we get zero, and that helps in the process quite a bit. But what if, right? So take a look at this example. What if we have, let's say, an exponential function times a trigonometric function, right? Like e to the x times the sine of x dx, right? Again, because it's a product, we can't just take the antiderivative of the e and the antiderivative of the sine and multiply them. Again, if it didn't work for derivatives, it cannot work for antiderivatives, right? Well, let's see what happens. So this is an e-type exponential, right? And this is a t-type trigonometric. And we know that the E is the last letter in Lie8. So sadly, the exponential function is always second best, right? And in this case, the trig will take precedence. So let's go through and try our process. Let's say we let u equals the sine of x, and then dv is going to be everything else, which will be the e to the x dx. So here I'm setting it up in that kind of formal way because I don't really see where the table will help. I mean, maybe it will help, maybe it won't, but at the very least we can set up our formal method and see what happens. So let's compute du. So du is the cosine of x dx, and let's compute our v. Our v is e to the x. All right. So then let's see what happens if we take we write down our original integral. That's equal to u times v, so it's the exponential times the trig function. So I'll write it as e to the x times the sine of x minus the integral of v du. Well, let's see what we've done. So we started with the integral of e to the x times the sine of x, and then we converted it into another problem where we have the integral of e to the x times the cosine of x. Not much has improved, right? Again, it's still a product. It's just a slightly different trig function. But you know what? Let's be stubborn. Let's do the integration by parts again. Let's do it a second time, right? So I'm going to use parts on this second antiderivative, the e to the x times the cosine of x, right? And as far as the choice, it's, we're back at the start. This is our e type. This is our t type, right? So we're going to choose u and dv in a very similar manner. The only difference is this one is cosine, right? So our u will be the trig function cosine of x, and the dv again will be e to the x dx. When I differentiate cosine now, I'll get negative sine, right? Negative sine x dx. And when I integrate e to the x again, I'll get back e to the x. So let's write down what we have now. So after 2 attempts, this is what we're going to have. So this is where we started. Here's our original integral. And you'll see why in a second it's important to always look back to where we started, right? It's almost like, you have to understand your past to prepare for the future. So we have our e to the x sine x. Then I have the minus. Now this minus is going to be applied to everything that I write down after it. So technically it's we're subtracting everything here, but I'm going to apply integration by parts to what's in the square brackets. So I'll have u times v. So again, I'll put the e first, e to the x cosine of x. Then I have another minus, and then it's the integral of v du. And this also has a minus sign. So you see, there's several negative signs here that we have to handle very carefully. Right, so we have that, and then dx, and then I'll close my square brackets. Okay, so that's what we have. So first, if I take this negative outside, then that becomes a positive. But then when I distribute this negative, it's going to switch everything back to negative. So it's going to look like this. So let's write it down with the negative sign distributed and the square brackets gone. So we have the integral of e to the x sine x dx is equal to e to the x sine x. And then again, with everything distributed, this will become a negative. So negative e to the x cosine of x. These two negatives will end up having a positive sign in front of the integral sign, but then distributing this negative now makes it negative again. So we will have negative the integral of e to the x sine x dx. Now, look at what we've done, or look at where we've ended up by doing integration by parts twice. The integral that we've started with is back. It's like mocking us. See, you can't get rid of me. And that's to be expected. Think about when you differentiate exponential functions. They stay the same, roughly, right? When you differentiate trig functions, eventually you get back to the trig function, right? Because it just cycles between cosine and sine, cosine and sine. And yeah, you have some negative signs in there, but essentially it just cycles back and forth between sine and cosine. So it's not that far-fetched to see the integral on both sides of the equation. So, but the question is, how does that help us evaluate the integral when the thing we're trying to figure out is on both sides of the equation? But the thing is, if we're clever, we think, okay, we're trying to solve for this integral. We're trying to figure out what the integral is, and we have an equation, right, that involves the integral. It happens to be on both sides of that equation. Why don't I try to isolate the integral? I know that sounds weird, right? But I mean, it's not that weird, because if let's say I call this I for integral, then it's right here as well. So if I write down this equation, and just for a second, just replace the antiderivative of e to the x sine x dx, just give it a name. Just call it something. Call it I, call it Fred, whatever you want to call it. But let's say we have I, and then that's equal to e to the x times the sine of x minus e to the x times the cosine of x minus I. If I gave you this equation and says solve for I, hopefully this is what you would do. You would add I to both sides, and then you'd have 2 times the integral that we're trying to solve for is equal to something that doesn't have an integral sign here, right? After I essentially collect all the integral signs on one side, right, I have this left over on the right-hand side. Right? So 2 times the thing I'm trying to solve for is this, right? Now, technically, this is where the plus c would come in, right? So technically there's supposed to be a plus c I'm going to go ahead and write the plus c there because we have the integral on one side and we actually have what its antiderivative on this side, but it's not quite done because we have 2 times the integral. And what we need is the integral by itself. So if I'm trying to solve for I, just divide both sides by 2. And then we end up with this it's this really clever solution to what seemed like a conundrum. It's like, we've entered some, circle of doom or something. But no, because where we started is right where we're back. All we have to do is we just have to make the connection and get the integral by itself. So then I is equal to 1/2 of all of this. Now, how do you want to write that? Well, you can write it like this. You could just put the entire thing as one fraction and then just put a 2 in the denominator. That works. You could do this. If you're like me and you like to have the coefficients out in front, you could then say that this is 1/2 e to the x sine of x, and then minus 1/2 e to the x cosine of x. And then again, as we saw in a previous video, anytime you have like a constant times another constant, or now a constant divided by 2, you can just relabel it and call it a different constant. You don't have to keep it as like c over 2. Just give it a different label, right? Because again, we don't know what the constant is. All we know that it is a constant. So you can call it C1. You can even call it K. Again, you can call it Fred if you'd like. But the whole idea is now that we know what our integral is. So let's do this. So let me switch it back to the integral notation now. So our original antiderivative of e to the x sine of x dx is equal to this, right? Right. Really, again, it's like a little magic, little math magic, where just through some sleight of hand, we're able to come up with this integral by really using algebra, but not exclusively algebra, because we had to do, the u and the dv, we had to do it twice in order to come up with this relationship. So it's not purely like an algebraic trick. Calculus took us here, and then algebra took us home, right? All right, so let's look at another example of something like this. And in this case, I'm going to show you how we can actually apply our table method to this. So here's another example. And this shows up so many times when you have like an exponential function. So let's try something like e to the negative t, and then let's say times the cosine of 4t dt, right? And I'm going to show you how we can use the table method, which we know is kind of a streamlined process whenever we have to do repeated integration by parts, right? So again, we have our e type, poor old e, right? And then we have our t type, right, which will take precedence over our e. So let's set up our table on this side. So we'll have a column for the u's, a column for the v's, and the u in this case is going to be the cosine function because the t comes before the e in Lie8, right? So we have cosine of 4t and then e to the negative 2t. So the thing about this is we know we can't just continue differentiating forever because we will never get to 0, right? In fact, even if you tried to like switch these around, it wouldn't make a difference because neither of these functions will ever get to 0 no matter how many times we differentiate them. The exponential function will just, there will be a constant that will either be multiplying or dividing this, whether you're differentiating or integrating. And the same thing with the cosine. It just switches back and forth between sine and cosine. The signs might change, right? And then the constant in front will change, right? But neither of these will ever go to 0. So the trick here, just like what we did above, is to do the process twice, right? So we're going to do our table and essentially have our table go down to 3 rows. So this original row and then 2 more rows. And then we're going to stop and we're going to see why, looking at that 3rd row, it makes sense to stop, right? So if I differentiate this once, I will get -4 sine of 4t. That's our chain rule in progress. If I differentiate it again, I'm going to get a -16 cosine of 4t, right? And it's the fact that I end up back with a cosine. That's an indicator that, hey, I'm pretty much right back where I started, only with a different coefficient in front, right? And that coefficient will factor in as far as the algebra is concerned, but from a calculus standpoint, the fact that we're back at cosine, it means we've essentially come full circle, right? So again, it's the idea of once this function shows back up in your table again, that's when you stop. Otherwise, it's just this infinite loop that you'll be stuck in, right? And then we integrate as many times. So the integral of e to the -2t is -1/2 e to the -2t. And then another integral to balance out our table is 1/4 e to the -2t. And then let's set it up. So we know the products that we need, this one and this one. And we also need our v du going across, but that's going to be an integral, right? It's going to be the integral of that product, right? And the other piece that we need to remember is to alternate the sign. So plus, minus, plus, right? Okay, so let's write down the equation now, and hopefully, and not hopefully, but we know we're going to get this integral on both sides. It's just a matter of how we do the algebra. We just have to do the algebra carefully and solve for this integral. All right, so we have our original integral e to the -2t cosine of 4t dt. That's equal to, so we have a positive here times this negative, so it's going to be a negative, and I'll put the 1/2 in front, so -1/2. Then we'll have the e to the -2t times the cosine of 4t. So that's my first arrow there, and that's just a product. That's just u, v. And we get another product here, and now we have a double negative, so that makes it a +4 sine of 4t times 1/4 e to the 1/2 or -2t. Now, because this coefficient is 4, this coefficient is 1/4, when I multiply them, I'll just get a 1. So I'll have a positive e to the -2t sine of 4t, all right? And then the last bit now is where we're going to get the integral. So we're going to multiply across, so that's our v du, but we have to take the integral of that. Now the coefficient will be negative, right? So because we have a plus and a minus there, and we have a 16 times 1/4, so that's a -4, right? So I'll kind of pull that constant outside, and then I'll have the integral, and what we have left is this, our same exponential times our cosine of 4t. So this pretty much confirms what we suspected when we saw the cosine of 4t in the table, is that, look, we are right back where we started, right? Just have a slightly different constant in front now, right? And that constant comes from, the fact that we had to differentiate twice and use the chain rule, and then we had to multiply these two together. So all that comes together, and we have this number in front, right? So again, if you like that idea of labeling the antiderivative as just an I, just to help you with the algebra, you can certainly do that. Right? So let's write the equation now in terms of I. So I is equal to negative 1/2 e to the negative 2t cosine of 4t plus e to the negative 2t sine of 4t and then minus 4I. So if we now try to isolate the I, we're going to add 4I to both sides of this equation. So I'll have 5I here. So now that I've collected the integral on this side, I'm not going to have an integral left here. So this is going to be our antiderivative once we put our plus c. So like that, and then plus e to the negative 2t sine of 4t, and then plus c. So that means the integral is all of this divided by 5. So our integral is, now negative 1/2 divided by 5 is negative 1/10 e to the negative 2t cosine of 4t. This divided by 5, this coefficient is 1, so we'll have 1/5 e to the negative 2t sine of 4t. And then again, dividing this constant by the constant 5 will give us a slightly different constant. Call it C1, C2, K, anything you want. Just don't use T, right? So let's say, I'll just call it C1. So here's our final and complete statement. So the antiderivative of e to the negative 2t times the cosine of 4t is equal to negative 1/10 e to the negative 2t cosine of 4t plus 1/5 e to the negative 2t sine of 4t plus our constant. All right? So these are interesting integrals because we do them twice, we get back to where we started, and we end up using algebra to solve for the integral, right? Good old algebra to the rescue, right? And you might be thinking, when am I ever going to use this? Well, I'll tell you when you'll use this. Whenever you analyze certain electrical circuits using differential equations, you end up, depending on the type of voltage source in your circuit, you end up doing integrals like this over and over and over again, right? So don't think that, again, this is just some made-up thing because we just love doing integrals. I mean, that's like the cherry on top. But no, these things show up when we analyze certain physical systems that have certain characteristics. So chances are, if you have a course in differential equations in your future somewhere, you're going to be doing this, but in a bigger context. So I'm sure you're looking forward to that. I know I am, as we are looking forward to the next video. Yep, I'll see you then.